All right, last time we talked graphs. We were talking position time graphs. This time we talked graphs, we were talking a slightly different graph, velocity time graphs, although the stories that these graphs tell are going to be drastically different. Looking at our very first example here. If this had been a position time graph like you had seen before, if I would cross this out and write in position, and this would be in meters, being that we're talking meters divided by seconds, the whole slope would equal velocity because we're talking meters per second. And all that means is that the position, as we, traverse our first 5 seconds, the position would have increased by 10 meters. And we would have sat at that 10 meter mark for 10 seconds. And then over the next 10 seconds, we would have stepped backwards 5 more meters. It didn't tell us anything about the speed or the velocity of the actual item until we calculate the slope. All that the graph right now is telling us is that you were moving forward, stopped, and then moving backwards. That, however, was for a position versus time graph. Today we are not dealing with position times, we're dealing instead with velocity versus time. And velocity, we've got that meters per second divided by seconds, which in all reality really means meters per second squared. So our slope equals acceleration. So what we see here is that as we are working, and the story of this graph, as we work from 0 to 5 seconds, the velocity is increasing, which means you are getting faster as you work your way up the slope of this graph. We start off at 0 meters per second. Halfway through, we're at 5 meters per second. At the end, we're at 10 meters per second. We continue to increase speed. This whole thing right here is an acceleration. We then stop accelerating. We have not stopped because at point B, or the segment B, from 5 seconds to 15 seconds, we are moving at a constant velocity. We're moving at 10 meters per second. So this is 10 meters per second right here, and this is 10 meters per second right here. What this is your constant velocity. Now you could have a constant velocity that is also stopped. That would be the case if you happen to have a horizontal line on the x-axis here. Okay, if this instead from here to here were our segment B, this would be two things. It would be a constant velocity, but that constant velocity would be 0 meters per second because that's where it corresponds on this y-axis. Anyways, we took a quick little side trip there. And then from this point where we're at 10 meters per second, moving all the way to our segment C, from here to here, we are decreasing in velocity, which really means we are slowing down. And again, we call that a deceleration. Right? Now, we can put numbers on all these things and figure out what they actually mean, how much you're accelerating, or at what rate you're accelerating, at what rate we are decelerating. But for now, just being able to tell the story of what's happening here. This would be you're at a red light, it turns green, you accelerate forward until you reach a rate of 10 meters per second, and then you continue at that rate for 10 seconds. And after 10 seconds of that continued rate, we're at 15 seconds total now, you start slowing down as you're approaching the car in front of you, and you're slowing down to a rate of 5 meters per second. And obviously, because we're still moving, being at 5 meters per second, this story isn't completely done. But for this graph, that's all we need to be able to do. Now, putting numbers on this stuff, being able to actually calculate the accelerations would be very useful. And in terms of doing that, for A, I found that your acceleration formula, Vf minus Vi all over t, is basically what we were looking at with the last graphs, the y2 minus y1 over x2 minus x1. The y2 minus y1, it's this. Okay, so the only thing that's really changed is now your t is just the change in time. So let's put some numbers in. For segment A here, we know our final velocity is going to be this 10 meters per second, as indicated by this right here. That's your 10 meters per second. So this is a 10 meters per second. And your initial velocity was down here at 0 meters per second. So we're going to have 10 meters per second over something. How much time did it take us to reach that 10 meters per second? Well, we went from 0 seconds to 5 seconds. So you're going to end up having 5 seconds. Throw all that in a handy-dandy calculator. 10 meters per second over 5 seconds. That'll give us 2 meters per second squared. So the acceleration for A is going to be 2 meters per second squared. Pretty decent acceleration. B, we could again put into that same formula. Acceleration equals VF minus VI all over T. But the fun thing about V, with it being a horizontal, I know the final velocity is 10 meters per second, and I know the initial velocity is 10 meters per second, which means whatever we do, it's 0 up top, which means your entire set is going to be 0 meters per second squared, because it's a constant velocity. There is no acceleration. And then the final setup that we have is your slope for C. Again, acceleration equals VF minus VI all over T. Looking at T, we are slowing down from 15 to 25 seconds. So this whole thing is our slow down time. So our time is going to be 10 seconds worth. Our initial velocity is going to be this 10 meters per second up here. And our final velocity is going to be that 5 meters per second over there, 5 meters per second. So 5 minus 10 gives us a negative 5 meters per second over 10 seconds. Otherwise, a negative 0.5 meters per second squared. So we are decelerating or slowing down at a rate of half a meter per second squared. All right. Moving on to our second example. Scroll our way down, we got a second graph, and as soon as we work our way through this, we'll call this video a day. First thing I'd like to talk about is just the story. What does this graph tell us? Now, in order to figure that out, the first thing I do is I look at each axis. This is time, so we know something's going to be changing over a period of time. We're talking 12 seconds. Look at my y-axis, and I know I'm dealing with velocity. So I know whatever's going to happen, the slope equals acceleration. So in terms of the story, this thing is speeding up from stopped to 20 meters per second, and that happens in 2 seconds. And then it stays at that constant velocity for 2 more seconds, and then it speeds up some more, accelerates again, up to 40 meters per second, and this time it does that acceleration in 1 second. We're going from 4, so 4 right there, to 5. So that acceleration is happening really rapidly. And then we stay at a constant velocity of 40 meters per second here, and then the item starts to slow down. And we decelerate from 40 to 20 meters per second, and that happens over from 8 seconds to 10 seconds, so we're gap at 2 seconds. It stays at a constant rate, constant velocity there of 20 meters per second, and then it'll increase in speed 10 meters per second from 20 up to 30, and that happens in 1 second. So in terms of our story, speed up, stay at the same rate, speed up some more, stay at that maximum rate for some amount of time, slow down, stay at that rate, speed up. And so once you figured out that story, from there we can actually start looking at how to solve for the slope of some of this stuff. And we'll try to cut out a couple of these real quick. But from A to B, acceleration equals VF minus VI all over T. I know that the VF is going to be 20 meters per second. I know the VI was 0 meters per second. and the time was 2 seconds. So this really gave us a 2 meters per second over 2 seconds. Your slope in this case is going to be 10 meters per second squared, which is pretty hefty acceleration. In terms of b to c, right, I know I'm going to have acceleration equals vf minus vi all over t. Throwing some numbers in, I know my final velocity is 20 meters per second, and my initial velocity is 20 meters per second. And it doesn't matter what time that is, even though it's 2 seconds, from 2 to 4. 20 minus 20 is going to give us 0, which means this whole ballpark here is going to be 0 meters per second squared. There is no acceleration. C to D, A equals VF minus VI all over T. Throw some actual numbers in here. VF, my final is going to be 40 meters per second. My initial is 20 meters per second. And all that happens over a span of 1 second, from 4 to 5. So over 1 second. 40 minus 20 gives us 20. 20 over 1 second means that this acceleration is 20 meters per second squared, a ridiculously large acceleration in terms of what we talk about generally. Again, at this point, hopefully you've realized that if we've got a horizontal line, like we do from D to E, it's going to look exactly like B to C, 0 meters per second squared. We are not accelerating at all, although we're still moving. We're moving at a very impressive velocity of 20 meters per second, which is a pretty decent rate. Our next setup, from E to F, A equals VF minus VI all over T. We know that when we put some stuff in here, by stuff I mean numbers, we're going from 8 seconds to 10 seconds, 2 seconds. Our final velocity is 20 meters per second, and our initial velocity is 40 meters per second. So we're going to end up with a negative 20 meters per second over 2 seconds, which is going to give us negative 10 meters per second squared in terms of the acceleration, which just means that we are slowing down. It does not indicate a direction at this juncture. Again, we have a horizontal line, 0 meters per second squared, nice, easy. And then our final one, from G to H. At this point, you should kind of mentally be able to throw some of these out. We know that it takes 1 second, and that we are traveling from 20, or a velocity of 20 meters per second up to 30 meters per second. That's a change. 20 to 30 gives us a change in 10. So we've got an acceleration of 10 meters per second squared. Hopefully this stuff makes a bit of sense. If it does not, try the extra help handouts, because there are some more velocity time graphs, including answer keys there.